Welcome to this lecture. This is the fifth lecture of week 5. In the previous lecture, we have introduced the concept of a characteristic function corresponding to a probability measure on R or Rn, and similarly we have extended the definition to the case of random variables or random vectors. We have essentially used the fact that given any random variable or a random vector, there is an underlying law which is a probability measure on R or Rn as the case may be, and then we have simply looked at the corresponding characteristic function. Afterwards, we have explored the basic properties of characteristic functions, especially the fact about continuity and differentiability. In this lecture, we are going to talk about the relations between characteristic functions and the probability measures, and of course in terms of the corresponding random variables. Our main question in this lecture will be this: suppose I have an unknown probability measure but with a explicit characteristic function, can I identify the underlying probability measure? This is what we are going to discuss in this lecture. Without further delay, let us continue the discussion using the slides. So, again we have discussed about these probability measures and corresponding characteristic functions, and we have extended the definitions to n dimensional random vectors. Now, we have discussed very basic properties. Here our first interest is to recover underlying probability measures from the characteristic functions. So, for simplicity we are going to work in dimension 1, but all these results can be stated with appropriate notational changes in terms of the higher dimensions. The first result that we are going to discuss is called the inversion formula. So, this is essentially a Fourier inversion formula that we are going to discuss. So, the setting is simple. I start with the real line together with the Borel sigma field, and let us say mu is a probability measure defined on that measurable space, and look at the corresponding characteristic function. Now, what we are going to also look at is the corresponding distribution function with respect to the probability measure, and this is again just for the recall. This distribution function is defined in this way that for all real numbers x, I look at the interval minus infinity to closed x and look at the size associated by the measure mu. This number is between 0 and 1 as mu is a probability measure, and that is taken as the value of the function at the point x, and this is what is the distribution function corresponding to the underlying measure. Now, here the result says that I can link this distribution function and the characteristic function, and this is linked in this way that for all a less than b, where the distribution function is continuous, fb minus fa must be equal to the limit of this integration. Now, let us try to understand this integration. So, first we are looking at the inside the limit. So, for all this c as c goes to infinity, we are looking at this specific type of an integrand involving the characteristic function and this interesting scaling involving certain terms involving the exponential functions, and we also scale the final integration by 2 pi here, and we are saying as c goes to infinity, this limit will be exactly f of b minus f of a. So, if I know the characteristic function explicitly, in principle I can compute the right hand side of this expression, and that is going to give me the value of the left hand side whenever a and b are 2 points a less than b and where f is continuous. Now, before going to prove this, let us make some observations. So, if I look at the distribution function corresponding to any probability measure, then the distribution function by definition is non-decreasing as well as right continuous. Moreover, if f has certain discontinuities, then this must be of the type jump discontinuity, and moreover the number of such discontinuities must be at most countable, meaning these are either finite in number or countable in number, and whenever there is a jump, that jump will be captured by this difference of the right limit and the left limit, and here the difference is exactly captured by the measure of this singleton set small x. So, here note that f is continuous, that will immediately mean that the right limit and the left limit matches, and hence this means that mu of the singleton small x, that must be 0. So, this is essentially trying to capture the jump discontinuities through the size of the singletons under the probability measures. Now, this earlier theorem can also be stated in terms of random variables also. So, what we do is that if we take any random variable x, then look at the corresponding distribution function f x and the characteristic function phi x, then the same result will follow just by looking at the probability measure mu, which is p compose x inverse. So, here what we are saying is that the difference of the distribution functions where a is less than b and at these points a and b, f x must be continuous. If we choose such a and b, then the difference of the distribution functions can be computed by these integration limits, and where the integrands involve the underlying characteristic function. So, in principle we are recovering the difference of the distribution functions using the known characteristic functions. So, this is essentially the interpretation. Alright. So, let us look at the proof of this earlier theorem in the general setting involving the measures, probability measures mu. So, here we are interested in looking at these type of integrations where our c is taken to be positive. Note that we are going to let c going to infinity. So, there is no harm in looking at only positive number c. So, for positive number c, I look at these integrals and denote it by I subscript c just for our convenience of notation. But now note that this characteristic function that I am looking at, that as per definition is given by an integration. So, I write this additional integration inside the existing integration. So, this is essentially some iterated integrations. Now, remember we have discussed about these iterated integrations where we have come across the product measures and integrations with respect to those, and we have used Fubini's theorem in order to make sense of many of these iterated integrations. So, here we have to ensure certain integrability conditions. So, before I look at these specific iterated integrations, let us first look at the integrability conditions which will help us make sense of this kind of iterated integrals in terms of double integrations, in terms of the underlying product measure. Let us see the integrability conditions. So, we start with modulus value of the whole integrand here. Now, first note that this term here exponential I u x, the modulus of that is 1. So, therefore, I can ignore it from this calculation. Now, here it is purely in terms of a and b, and here this expression inside the modulus can be thought of as this integration, and here this can further be dominated from above by this quantity. So, there is a minor typo here that will be corrected in the lecture notes. So, here again I use the bound that this term is dominated from above by 1, and therefore, this quantities can be dominated, my left hand side can be dominated by b minus a. So, here you see the left hand side has a bound independent of small x, this is given by b minus a. Now, if I observe this, then for any c positive, if I do a further integration outside involving this non-negative function here, then I immediately end up with the fact that since I am integrating non-negative function, then for any iterated integrations there is no problem because we can appeal to the Fubini's theorem. So, since in this situation we are working with modulus of this complex valued functions, this is non-negative. So, here I can always perform the calculations in either way I want. So, let us go back and check this. So, here I am now using the upper bound given by this b minus a. So, that will come outside the integrations, but note that this inner integration will again turn out to be 1 because this is measure of the real line under the probability measure, and therefore, this whole expression can be dominated by 2c times b minus a, and that is a finite quantity, and therefore, for every fixed c positive I have obtained these integrability conditions. So, therefore, we can look at the Fubini's theorem and do these simplifications. Here you also have to notice that this integrand here can be simplified further in this way, that this is first of all the difference of these two exponential terms, but if I split in terms of the cosine and sines, the real parts and imaginary parts, I will end up with this kind of differences. But then I am essentially going to divide that integrand there by u. So, we are going to look at these kind of functions inside the integrations if I split the real part and the imaginary part. So, in particular if I look at the real part, which is consisting of this expression where I am looking at this difference of the cosines and divided by u. Here the cosines are even function, but whenever I am dividing by u, this whole expression turns out to be an odd function whenever u is taken to be non-zero. This is just to ensure that I am not dividing by 0, but whenever I am doing these integrations, these are in terms of the Lebesgue measure, and here not knowing the value at 0 is not a problem, because Lebesgue measure associates 0 mass to singletons, in particular to the origin singleton set. So, therefore, here we can go back to the Fubini's theorem argument and exchange the order of integrations. So, we can now simplify the integration IC that we have introduced earlier. So, here this simplifies because the real part does not contribute anymore. So, that is the cosine terms do not contribute, but here this simplification turns out to be only involving these sine functions now. So, here we have to simplify these expressions. Now, here our final thing that we are going to perform is to take the limit as c goes to infinity. So, here what we do first is that we look at this integration this limit now. So, first note that if I take this kind of a limit, so here we are for the moment ignoring the integration of the real line that is outside. So, inside the definition of the integration IC, there are two integrations, one involving the R, one involving the Lebesgue measure. So, the first one is in terms of the probability measure, the inner one is with respect to the Lebesgue measure. So, what we do first is that we first look at the integrations involving the Lebesgue measure and take the limit first. So, what we would like to claim, if we take the limit as c goes to infinity, we can take the limit inside the integration involving mu. So, first let us look at this pointwise limit. So, the claim is the pointwise limit can be explicitly computed, and this is exactly the case that whenever x falls in this range, this quantity is exactly 0. If x is exactly a or b, this quantity is half, and if x is inside a b in the interior, then this quantity is 1. So, you can check it explicitly, this is left as an exercise for you. But here this expression essentially depends on x. So, you end up with a function of x. This function of x has this very nice form that whenever it is inside a b, this gives you the value 1. So, this is expressed in terms of the indicator function. Whenever we are looking at the singletons a and b, this will give you the value of. So, that is why we end up with this expression here. Now, look at this limit, and by appealing to the dominated convergence theorem again in connection with the Fubini's theorem, taking c going to infinity, we end up with pushing the limit inside the calculations. And now, we have computed the inside limit, which is exactly this function involving x, and we just have to perform the final integration with respect to the underlying probability measure, and which is going to give us this expression, that this is equals to mu of open a b plus half times mu of a plus half times mu of singleton b. But note here that we have assumed that we are working with a and b such that the continuity of f is there. So, therefore, mu of the singleton must be 0 and mu of singleton b must be 0. So, therefore, this earlier limit can also be rewritten using this expression. This is no change because this quantity is anyway 0. Now, here note that open a b together with the singleton b is going to give us the left open right closed interval a b, and that essentially is linking us to the difference of the distribution functions values at b and at a. So, that is how we have managed to establish the result that we have claimed earlier, and this completes the proof. So, here we have crucially used the Fubini's theorem, and we have used this exchange of integrations by ensuring the appropriate integrability conditions. We have also ensured the limiting operations are true by appealing to the dominated convergence theorem type arguments. Now, using this result, we are going to look at the recovery of underlying probability measures if the characteristic function is given. Now, this is our next result. So, it says that the characteristic function uniquely determines the underlying probability measure, namely if mu and nu are two probability measures on the real line together with the Borel sigma field such that the characteristic functions match pointwise, then the measures must match in the sense that they associate the same value for all Borel sets. So, this says that the measures must be equal. So, mu equal to nu in this setting. So, we are simply saying that as long as the characteristic functions match, the corresponding probability measures must match. Before we discuss the proof, there are some important comments that we would like to make. So, first we can state this version of the theorem in terms of random variables. It goes like this, that if x and y are two random variables such that their characteristic functions match on the real line, then x and y must be equal in law or equal in distribution. We can also say x and y has the same law. So, here we have to note that the random variables x and y may be defined on different probability basis, but we can still look at the corresponding characteristic functions, and if these characteristic functions match, then x and y are equal in distribution. We also make another note that this theorem 9 and the remark that is discussed in the one dimensional setting, but this can be extended to the n dimensional setting. So, we are not going to restate the results, and these statements can be easily restated. Please take this as an exercise, but again all these results follow by general arguments that we are going to discuss in one dimensions only. These explicit arguments can get extended using appropriate notational changes, and we will get the general versions in the n dimensions. So, let us see the proof of theorem 9, that we are now given two probability measures with the same characteristic functions, and we would like to claim that the measures match. So, here what we do is that we look at these two probability measures and look at the corresponding distribution functions. Now, these distribution functions are right continuous, non decreasing. So, in particular they will have possibly certain jump discontinuities. So, let us look at the set of jump discontinuities. So, we will denote that set of points to be d mu and d nu, where these jump discontinuities occur for f mu and f nu respectively. So, here note that each of the sets of jump discontinuities, each of them are either finite or countable infinite. So, therefore, if I look at the union of these two sets, that is also finite or countable infinite. So, therefore, we end up with this fact that union of d mu and d nu is at most countable. Now, let us look at this general situation, that if I look at the complement of this countable set, then if I pick up any point there, then both the distribution functions are continuous at this point x. Now, what we do is that we fix any two real numbers a and b with a less than b. Now, since this union of the two sets d mu union d nu, that is at most countable, I can construct sequences a n and b n from the complement of this set such that a n decreases to a and b n decreases to b as n goes to infinity. So, I will be able to construct such specific sequences coming from the complement of this at most countable set. So, now what we are going to look at is that the fact that a n's and b n's are coming from the complement of these union of the discontinuities of the distribution functions at the points a n and b n, the corresponding distribution functions are continuous. So, let us now appeal to the inversion formula that we have discussed earlier. So, let us start. So, I look at the measure of the left open right closed interval a b. So, remember here a and b are any two real numbers that we have chosen, but with the relation a less than b. Now, this quantity measure of left open right closed interval a b, that is given by the difference of the distribution function values at b and at a. But now, since the distribution function is right continuous, using the right continuity of the distribution function, we simply claim that as Bn decreases to B and An decreases to A, then this quantity will go to this quantity and this quantity will go to this quantity, and therefore, we can rewrite in terms of the limit of these difference of terms. But here at An as well as Bn, the distribution functions are continuous by construction, and therefore, here we can appeal to the inversion formula, and here I just simply bring in the underlying characteristic function corresponding to the measure mu, but here I have to use these points An and Bn. So, please be careful with this step. But now note that the two characteristic functions corresponding to the two probability measures given to us are given to be equal. So, I just change this in this step, no other expression is changed. But now I will just go back using the same set of arguments again by the inversion formula. I now look at the difference of the distribution functions value, but with respect to the measure nu. So, here again I appeal to the right continuity because Bn goes down to B and An goes down to A. So, again by right continuity I end up with this expression, which is exactly the new measure of the left open right closed interval AB. So, therefore, we have managed to show that for all A less than B in the real line, measure of left open interval AB are the same with both measures mu and nu. So, more generally I can extend these ideas by finite additivity to finite disjoint unions of such left open right closed intervals, and since this collection of sets forming a field which generates the Borel sigma field, by the principle of good sets or by appealing to the characteristic extension theorem, we will be able to conclude that mu of A equals to nu of A for all Borel sets. So, therefore, the two measures must match. So, this essentially tells you that if two probability measures are having the property that their characteristic functions match, then the probability measures must match. And we have also discussed the same result involving random variables. So, the setting is this: if two random variables are given to us, even if they are defined on different probability spaces, as long as they have the same characteristic function, they will have the same law. Now, let us take this as an exercise that I am giving you a probability measure on the real line, but with the additional condition that the characteristic function with respect to the measure mu is integrable with respect to the Lebesgue measure on the real line. This simply means that the integration mod phi mu, that quantity d lambda, that should be finite. So, this is the integrability condition being assumed here. Now, under that assumption I look at this integration. Here the integration is with respect to the Lebesgue measure only, Lebesgue measure. So, now we are looking at this expression. So, note that this term here has modulus 1. So, again the relevant integrability applies and this integral therefore exists. Now, for all such real x, I assign the value of the integral to this function. So, that is how I end up with a new function which we denote by small fx. Now, check that under the condition of the relevant integrability of the characteristic function, this new function small f must be non-negative and continuous. Moreover, if this new function small f is integrable with respect to lambda, then the characteristic function can actually be recovered by an integration involving this new function small f. So, this is essentially going back and forth between the characteristic function and the new function small f. This is essentially using the Fourier inversion techniques all over again. So, but here we require the integrability of the new function small f. Alright. So, these two statements you try to check, but moreover from these statements we also get some interesting observations that if I choose two real numbers a b where my distribution function is continuous and a is less than b, then the integration of small fx dx over a b, now using the expressions that we have obtained, is given by these iterated integrations. This is just following from our discussion that we had in terms of the exercise, and therefore we can simplify this further and I end up with this expression, and this expression by the inversion formula is exactly the difference of the distribution functions at b and at a. So, therefore, the difference of the distribution function is recovered in terms of the non-negative continuous function small f over the interval a b, and therefore, this can be further extended to an equality involving all a b in the real line, not necessarily only looking at a b where the distribution function is continuous. So, please check this step. And moreover, this identification will give you therefore that this function small f is therefore giving you a probability density function corresponding to this distribution function. So, again if the characteristic function is integrable with respect to the Lebesgue measure, I essentially am able to recover the density function, but with essentially additional integrability conditions, provided the function that I have obtained is further integrable with respect to the Lebesgue measure once more. And finally, we make some small observations involving properties of characteristic functions, that if I start with any random variable x, then the characteristic function of minus x can be computed in terms of the characteristic function of x just by looking at the complex conjugate. And this relation we will typically write in this way, that phi of minus x is the complex conjugate of phi x. Now, observe that if x and y are independent random variables, then the characteristic function of x plus y, that can be written in terms of their expectation, and that will essentially split in terms of an integration involving x and integration involving y, and therefore, we will end up with this product of the characteristic functions. So, therefore, if the two random variables x and y are independent, then the characteristic function of x plus y is given as the product of the individual characteristic functions. And using these observations, we also have this very nice interesting fact that if x and y are independent random variables, remember first of all independence can only be discussed if both the random variables are defined on the same probability space. Now, moreover, we also put this additional assumption that the random variable y has the same law as minus x. Then what happens is that we just look at this part 1 and 2 that we have discussed here. So, first we use the independence to say that characteristic function of x plus y is the product of the characteristic functions, but characteristic function of y will be given by complex conjugate of phi x, and that essentially is giving us modulus of phi x squared. So, here in this setting, modulus of phi x squared is the characteristic function of x plus y with x and y as above, meaning x and y are on the same probability space, they are independent, and y has the same law as minus x. Now, I give you this interesting exercise that first I look at any random variable x on some probability space omega f p, construct a possibly new probability space denoted by omega tilde f tilde and p tilde, and new random variables on this new probability space y and z with these three properties, that y and z are independent, y and minus x have the same law, z and x has the same law. Now, if you use this exercise, what we are going to get is that if I start with any random variable x, then I can look at the corresponding characteristic function phi, right. So, whenever phi is the characteristic function of some random variable, I will be able to construct some other random variable on some probability space which has the law as minus x. So, that is going to give us the phi bar will be the characteristic function of the new random variable that I have thus constructed. So, therefore, whenever I start with any characteristic function, I can always get that the conjugate is always a characteristic function. Again, I can repeat the same argument with modulus of phi squared. The idea is whenever I have x, I can now construct these two random variables y and z with the property that y and z are independent, y has the same law as minus x, z has the same law as x. So, therefore, if I look at the characteristic function of y plus z, that is exactly mod phi squared. So, therefore, we can always say that if I start with a characteristic function phi, then immediately I will have the fact that mod phi square and complex conjugate of phi are characteristic functions. These are giving us some nice properties of transformation of characteristic functions. In the next lecture, we are going to discuss problems involving the discussions that we held in this week, especially involving the convergence of random variables and the characteristic functions. This is what we are going to discuss in the next lecture. We stop here. Thank you.